Hi, my name is Manish Gupta, and in this video, I'm going to talk about the Google PaLM model. This is a model which has scaled significantly using their pathway system. So in this video, we'll talk about the PaLM model, its architecture, the pathway system, and then the applications of the PaLM model in terms of improving the accuracy of various NLP as well as NLG tasks. Let's get started. So what is PaLM? PaLM is a 540 billion parameter densely activated transformer language model. 540 billion, so that's a large number, right? It's pre-trained on 780 billion tokens. So again, pre-training has been done very rigorously. And the most important thing, it has been pre-trained using more than 6,000 TPU v4 chips using their system called as Pathways, which is a new machine learning system for highly efficient multiple TPU pod kind of training. Okay? So TPU stands for Tensor Processing Units. PaLM is related to other similar models like GPT-3, GLAM, Chinchilla, Gopher, Megatron, Turing NLG, Lambda, and so on. PaLM achieves a training efficiency of 57.8% hardware flops utilization. Flops is floating point operations, right? Which is the highest yet achieved for large language models at the scale of 540 billion parameter. Here are some of the achievements of the PaLM model. So when it was proposed early 2022, it was shown as the state of the art. It provides state-of-the-art few-shot learning results on hundreds of NLU and NLG benchmarks. It led to steep performance increase for big bench tasks. It is also really great at multilingual NLG and source code generation capabilities, as we'll see in the later part of this video. It generates explanations using chain of thought prompting for explaining jokes or logical inference. Again, we'll see some examples. So they train three different checkpoints for PaLM model, 8 billion, which is the smallest one, 8 billion parameters, 62 billion to 540 billion parameters. The number of layers, as you see, essentially increase up to 118 layers, effectively transformer layers in a PaLM 540 billion parameter model. And then, accordingly, the D model and the number of heads also increase. Now, as you see in this little animation here, what you observe is that as you increase from the 62 billion, 8 billion parameter model is very small. It can only do question answering, arithmetic, language understanding, but 62 billion parameter model, more and more natural language understanding, logical reasoning capabilities start showing up until it reaches a 540 billion parameter model, which is capable of doing so many different tasks, right? Translation, common sense reasoning, code completion, general knowledge, reading comprehension. As we will also see these more in the video as we talk. So how does PaLM's model architecture look like? Well, it is a transformer decoder only model. It uses, rather than ReLU activation, it uses SWIGLU activation, which is based on GLU functions with the swish function. Okay? It has parallel layers, so which basically means that while in a typical transformer, you first apply attention, and then on top of that layer norm, and then an MLP on top of that. Well, in parallel layers method, you effectively apply the MLP part and attention part in parallel, right? So that's that. It also has multi-query attention, which basically means that while in a typical transform model, um, for every head, there is a query key and value vector created. But in a multi-query attention kind of a scenario, you share the same keys and queries across heads, only the value is different. So that's that. It also uses rope embeddings rather than absolute or relative position embeddings, shared input-output embeddings. So the vocabulary embeddings at the input and output are shared, no biases. So anywhere in the model, neurons don't have biases. The tokenization is basically sentence piece with 256K token vocabulary, where white spaces are also preserved. They use a max sequence length of 2048, and they use this sequence length very, very efficiently by always packing every instance up to a size of 2048 and putting up delimiters in between to recognize instance boundaries. The pre-training was done using a 780 billion sized corpus, 780 billion tokens, and the data sources are pretty diverse in nature, as you see. So social media conversations, multilingual, filtered web pages, again multilingual. Social media conversations make up 50%. Books, 13% of the total data. GitHub code, 196 GB of code, okay, which is about 5% of the entire corpus. Well, they also have news and Wikipedia data included in the pre-training part. So the pre-training is done using Pathways system. So Pathways is their new machine learning system, which allows for cross TPU training, cross pod training, right? So they used two TPU v4 pods, and which are connected using Google data center kind of connections, right? Google Data Center Network connections using a combination of model and data parallelism. They do both. Right? Each of the pod basically has 3072 TPU chips, and they are attached to 768 hosts. So lots of hosts, lots of chips, pretty large scale. Right? Pathways follows a client-server architecture. So as you see, there are two pods here, the orange pod and the blue pod. And what you see on as large boxes are hosts. So there are several hosts, in fact, 768 hosts per pod. Then there's the scheduler host as well, which basically schedules the jobs in each of these pods, both of the two pods, right? So the way this works is that there's a Python client function, and of course the hosts in the pods are connected through this data center network. So the way this starts is that a Python client function dispatches half of the training data to pod 1, half to pod 2, and both of these pods actually individually execute the forward and backward computation to compute the gradients in parallel, right, using standard within pod data and model parallelism. So both of them do their own work separately, right? This work is denoted as A in this picture. They compute gradients, forward and backward pass, and so on. But then they have to also send that partially computed gradients to the other pod. And that is why in the second part, the pods transfer the gradients with the remote pod. And finally, each pod sort of accumulates its own computed local gradients and remote gradients that it has gotten from the other pod to obtain bitwise identical parameters for the next time step. Okay. So once that transfer happens, essentially, the process B kicks in the sense process B essentially transfers gradients to the other pod, remote pod, and then updates happen. Right. In fact, when cross-pod transfer is happening, cross-pod gradient transfer only happens one-on-one between the corresponding hosts on the two pods. So every host does not need to know, the gradients from every host in the other pod. So just one-on-one transfer happens. However, this traffic is pretty bursty in nature. After the entire computation forward and backward pass have happened, that is when you will suddenly have a lot of transfer going on. So this leads to huge traffic or requires huge bandwidth, and that is why a data center network provides this interesting bandwidth. The bandwidth can be, up to 1.3 GB of gradients in every training step between a pair of hosts. And so if you have 768 hosts, 768 pairs of hosts, then you can multiply that one, and then you will suddenly realize that you have like TBs of data being sort of transferred across hosts, across the two pods in a bursty manner. Okay, so how does PaLM perform with all of this awesomeness, right? All of the pre-training part and the large infrastructure that they've used to train. How does PaLM perform on popular English NLP tasks? They basically measured on several tasks. So on open domain closed book question answering tasks like trivia QA, these are data sets, trivia QA, natural questions, web questions, close and completion tasks, Lambada, Hela, Swag, story close, and so on. Vinaigrette style tasks, common sense reasoning tasks, in context reading comprehension tasks, superglue, NLI. So they've essentially measured across so many different tasks. And what they observe is that compared to the prior state of the art, PaLM 540 billion actually beats them all. In fact, it beats on 24 out of 29 tasks in one shot setting. So one shot setting basically means you just give one example, right? And then on 28 out of 29 tasks in a few short settings. So if you give a little more examples, well, 540 billion, PaLM 540 billion is hands down better than prior state of the art. Remember, this prior state of the art is April 2022. So now with the other models coming up, this may not be the best, but still, it's pretty good compared to many other existing models. So PaLM 540 billion is also, in fact, better than Megatron Turing NLG model, which was 530 billion parameter model. So which is also like a similar sized model, but still PaLM 540 billion is actually better. Here, what you observe is that across different tasks, natural language inference, common sense reasoning, and so on, the improvement on SOTA can be as high as about 8 points, which is huge, right? So it's not just better, but it's significantly much better. Okay. So MMLU or Massive Multilingual Language Understanding is a benchmark of 57 different tasks spanning topics such as mathematics, history, and law. How does PaLM perform on this benchmark? Well, here are the 5 short results. So you give 5 examples and then also the test example for it to predict. So as you observe, compared to GPT-3 or GLAM model, PaLM models actually perform really well. So in fact, here is so here we basically see the split across these 57 tasks on NLG as well as NLU tasks. So in fact, this is not completely 57. These are 29 tasks. So 21 NLU, 8 NLG tasks. And what you observe is that PaLM 540 billion improves on average score in both the categories by 5 points. So by 5 plus points, right? 63.9 compared to the best, which is 58.4, or 74.7 compared to the best, which is 68.7. Yeah. Also, if you basically compare it with other models like Chinchilla, what you observe is that in different 540, these 57 tasks basically are of different types: humanities, STEM tasks, social sciences, and other. And you observe that in most categories, except for the others category, PaLM model actually is way better. So how does PaLM perform on big bench tasks? So big bench is another benchmark, NLP benchmark with 150 different tasks that cover a variety of language modeling tasks, including logical reasoning, translation, question answering, mathematics, and many others. Yeah. Um, so here is a plot which basically shows how does it perform on a set of 58 tasks. So Big Bench, of course, has 150 tasks, but then initially only 58 tasks were released. And that is why several people have reported results on just those tasks. So on those initial tasks, these are the results. On the entire 150 tasks, these are the results. Okay. So what we observe is that here we are basically increasing the number of parameters. Remember, PaLM model has 3 different sizes, so that's the scaling curve. So as you increase the number of parameters, what happens, right? And also, what you observe is that you have PaLM models with different shots, so different number of different number of examples being given to the PaLM model to understand the task, right? So what you observe is that there is the best human performance here. So best human performance is actually way better on Big Bench, right? But this is the average human performance. And then what you also observe is that the blue curves, which are the PaLM curves, are actually doing really well compared to the other curves or other models like Chinchilla, which are comparable but not better. Okay, so what you observe is that PaLM 540 billion, 5-shot state-of-the-art model, 5-shot is better than the state-of-the-art model on 44 out of 58 common tasks. So out of these, this is basically average across all those 58 tasks. But if you take 44 of those tasks, PaLM model is actually better than the state-of-the-art. Uh, um, Also, PaLM 540 billion model, and also if you look at the 150 task thing, as you increase the number of parameters, you observe that, of course, the PaLM model gets better. So in fact, 540 billion parameter model is actually better than an average human. Right? Here is a more drill down across tasks. So this chart basically shows, on the x-axis you have tasks, on the y-axis you basically have is PaLM better or human better, right? Across 150 tasks. So what you observe is that for these blue tasks, of course, PaLM is better. For these orange tasks, human is better. And the idea is that PaLM 540 billion model is better than average human on aggregate, but average human is better than PaLM 540 billion on 35% of these individual tasks. In fact, the edge that PaLM model has is that it can understand several languages compared to an average human who understands only a few. So for example, PaLM is much better on multilingual tasks like Persian idioms and Swedish to German proverbs. Right? PaLM is also better on tasks which require a lot of memorization. For example, periodic elements task, and an average human does not really remember the periodic table of elements that well. Okay, so how does PaLM perform on reasoning tasks? PaLM was evaluated on 2 kinds of reasoning tasks: arithmetic reasoning and common sense reasoning. Arithmetic reasoning tasks include grade school level natural language math problems, word problems, so to say, which require multi-step logical inferencing. So the problems by themselves mathematically are not difficult, but conversion from word problem to the mathematical formulation is basically what involves the natural language processing. They tried several arithmetic data sets, these ones, GSM 8K, which is very popular, and so on, right? So they augment the model predictions using a post hoc external calculator as well, which is also very common so as to solve these mathematical problems. For common sense reasoning, these tasks are question answering tasks, which require strong world knowledge and require chaining multiple logical inferences. So it's not like you just have some facts somewhere and you use them, but hey, it requires chaining of these logical facts so as to essentially get the answer right. They have used 2 different common sense reasoning data sets, common sense QA and strategy QA. And then they also basically used a chain of thought prompting, because chain of thought prompting has been shown to give better results compared to standard prompting. So here are examples of standard prompting and chain of thought prompting. So in standard prompting, you can basically just say, here is the question: Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? Answer is 11. Okay. And then if you just do standard prompting, For a new example, the answer may go wrong. But with chain of thought prompting, people have actually shown that the accuracy is much better. So here the input is the same, but then in the chain of thought prompting, you also come up with explanations or show the chain of thought to the model, using an example. This is an example which is fed for the model to learn from, or more such examples. So rather than just saying that the answer is 11, you essentially say Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls, 5 plus 6 is 11, therefore the answer is 11. Okay. And when you apply the chain of thought prompting to a new question, it turns out that also generates an explanation, plus it basically comes up with the right answer. Okay. So having said all this, so on these reasoning benchmarks, basically here are the results, right? And the interesting part is that yes, PaLM achieves new state of the art on many of these data sets. It's not just better. I mean, of course, it's not just better overall, but it actually improves significantly on at least 4 of these data sets. Okay. So as you observe, these are, you see results here, which is this gray horizontal line is best state of the art. And the blue dotted line, blue dashed line is basically the direct prompting, and the blue solid line is chain of thought prompting. So clear observation, chain of thought prompting helps, right? Across all of these tasks that you see, chain of thought prompting is giving you better results. And what you also see on the x-axis is scaling. So 8 billion, 62 billion, 540 billion. So clearly it is also observed that as you increase the size of the model, typically you get better results. In fact, you get much better results by scaling from 8 to 62 billion. And then yes, after 62 to 540 billion, some of these tasks actually see really good results, but some of them basically saturate. Yeah. And as you see, compared to state of the art, at least on 4 of these tasks, PaLM model is doing better. PaLM model is doing better. So how does PaLM perform on coding tasks? They evaluated on 3 kinds of coding tasks: text-to-code task, code-to-code task, and deep fix code repair. So what are these tasks, right? So text-to-code task is basically evaluated on 3 benchmarks, and the task is very simple. You have text description, you want to generate code. So human eval and MBPP, the input is English description of a few sentences and a small number of input-output examples for the model to understand what to do, right? And the output expected is code, clearly, right? GSM 8K Python task is basically derived from the GSM 8K arithmetic benchmark, and the input is therefore a math word problem, and the output expected is Python code. Okay. So that is that. So for example, this is an example of a prompt and the output from the model. So here is a math word problem. Mary ordered 1 chicken meal that costs $12, 5 packs of milk that cost $3 each, 4 packs, and so on and so forth, right? And then the model actually outputs a program so as to essentially compute the number of boxes of pizza that Mary ordered if the box costs $8.5. So that's an example of GSM 8K Python task. Now, here are other examples. So, or the second kind of task is code-to-code task. And here the idea is to do translation from one programming language to another. So the specific example they considered is C++ to Python. And here is an example of that. So you have a C++ code, or more like a C code, right? And then you want to translate it to Python. This is a part of a popular dataset called as transcoder dataset. The third kind of also, there are other examples. Another example. So here's a prompt which basically gives you this is a prompt from human eval dataset. So a human basically, or the input is basically English description, and the output is supposed to be a nice code, which basically does what is mentioned in the English description. The third kind of task that they consider, example is not here on the next slide or later, right? They consider deep fix code repair, where the idea is that you start from broken student-written C programs that fail to compile, so there are compilation errors, and the objective is to modify the program so that they compile successfully. Clearly, you do not want to rewrite the entire program. You want to only make small changes. So ideally, we only want to modify a small portion of the broken code. Yeah. Here are results. Let's basically see how does it compare with other models. What are the other models to try out on code, right? For all the 3 different coding tasks that we discussed. Lambda 137 billion is basically not specifically trained for code, but has been shown to give good results from a code generation perspective. Codex model, of course, has been known to be specially trained for code and gives really good results on code previously, right? And then PaLM Coder is their own model, the PaLM model fine-tuned for code. We'll talk quickly about how it is fine-tuned, but that's fine-tuned for code. And then there's a 540 billion PaLM model. So as you see, the total code tokens that are used to train Codex model is basically 100 billion, of which approximately everything is Python. PaLM model 39 billion code tokens, PaLM coder model specifically trained on 46.8 billion tokens. So the way PaLM coder model has been tuned is as follows: two fine-tuning stages with 5.9 billion Python code from extra Python data. So the data set called extra Python data, and they basically use that data set 5.9 billion tokens from it to further fine-tune the PaLM model so as to get the PaLM coder 540 billion model. So they use two different fine-tuning stages, with different proportion of Python code versus other code versus typical NLG data, and that is how they fine-tune the PaLM coder. So let's look at the results. So basically, these are results on the first kind of task, which is the code generation task. So and well, there are also results about deepfix and transcoder here, right? So what you observe is that a PaLM is better. And you observe results about pre-training only and after code fine-tuning. So these have been compared with the Codex model and then the DaVinci Codex model, that is Text DaVinci 001, which was available to them. And that's the PaLM model, PaLM coder model, right? And what you observe is that the PaLM coder model actually gives you really good results across various tasks. For example, human eval, it is the best model. Yeah, MBPP, it sort of misses by a slight amount, but then if you look at transcoder, well, it is really good at translating from C++ to Python. PaLM is, of course, so PaLM is, of course, better compared. I mean, at pre-training time itself, PaLM is actually better than Lambda. So if you just compare the pre-training models on the left of this line, right, you see that PaLM is better than Lambda. PaLM is, in fact, also better than Codex, which is really, really good, right? PaLM is better than Codex, which is a really awesome model trained by OpenAI, but PaLM is better than Codex on human eval. Yeah. So those are some of the observations there. Now, if you look at the model scale, so clearly, if you increase from 8 billion to 535 billion or 540 billion kind of range, you observe that PaLM performs better at both parset-k and parset-1 metrics. So parset-k metric basically is used for code generation evaluation. It basically means if I use the model to generate k different samples of code, at least one of them, if it passes, if it does what the model is supposed to do, then you say that the model has a win. Okay. So compared to several other models, what you observe is that when you compare with several data sets, what you observe is that each data set sort of shows improvements as you increase the scale of the model, And these, of course, improvements show up in PaLM coder also. So as you increase the scale of the model for the PaLM coder model, you observe that across data sets, you get better and better results. Here is an example of a code being fixed. So remember this particular task, deep fix code repair. So here is some code, some C++ code, which is written out here, and then some C code, which is written here, and there is another code, and this is basically being fixed. So as you observe, several compilation errors are being fixed. For example, undeclared variables are being declared appropriately. So n, count, and so on. Yeah. You also observe the other stylistic improvements like declaring variables together. So they've all been put together. Logical improvements like reading numbers into array A in a loop, right? Reading them in a loop and not using index I outside the loop, right? So those are logical improvements. So basically, the model sort of improves significantly in terms of the code quality, and also, of course, leads to a compilable code. Okay. So now let's talk about other details about this code repair. So in code repair, they are you're comparing pre-training only and code fine-tuning. So essentially, pre-training only contains PaLM 540 billion compared with Lambda, and code fine-tuning consists of PaLM coder compared with DaVinci Codex model. So what do we observe? We observe that for pre-training only, of course, the PaLM model is hands down, way better compared to Lambda model. So somehow Lambda model just does not know how to sort of fix the code, Right? Well, the metrics that you see here are very interesting. So compile rate, what is the probability that after you, do the repair, the model will compile. So in 74% cases, PaLM model is able to give you a compilable code. PaLM coder is actually even better. Yeah. And Then what you also observe is in cases where the normalized edit distance is less than 0.1, what is the quality? Yeah. Versus when number of lines changed is less than 567, what is the quality? So the idea is you want basically the code to be fixed while you make as less changes in the overall code as possible, either measured as edit distance or measured as number of lines changed. Okay. So what you observe is that in the fine-tuning part, Palm Coder is actually better on all of these metrics compared to DaVinci Codex on the normalized edit distance matrix. Right? But on the line-based metrics, so how many cases did the code compile after you fine-tuned using Palm Coder or after you used Palm Coder or Codex models? If you care about lines changed, so only look at those test cases where less than 5 lines changed, less than 6 lines changed, so on. Unfortunately, Palm Coder model does not perform that well. Codex model is actually better in those buckets. Uh, this basically means that Palm Coder model tends to change fewer characters spread across more lines compared to Codex model. But then, these guys also mentioned that, hey, you can actually have some little tweaks so as to have Palm Coder model make small changes in less number of lines and therefore try to do away with this drawback as well. How does Palm perform on translation tasks? Well, they tried 3 different kinds of translation tasks: English-centric tasks, basically, which involve English language as one of the languages in the pair. So English, French, English, German, English, Romanian, and so on. Direct language pairs. So basically, they also tried French, German, and so on, which do not involve English at all. And extremely low language resource pairs. They specifically tried with Kazakh as a language. So what you observe here is essentially 0-shot results, 1-shot results, few-shot, and supervised results. Of course, Palm does not depend on supervised results, but supervised results are here to show what is state of the art in supervised learning. So the comparisons that you see are prior to the art and Palm 540 billion, prior to the art and Palm 540 billion. So what you observe is that Palm 540 billion is typically better compared to prior state of the art, no matter whether you do 0-shot, 1-shot, or few-shot. Okay. So Palm outperforms all baselines, sometimes with up to 13 blue points of difference. So what is plotted here is the blue scores. So what you observe also is that for DE English, for German English and Romanian English, actually Palm performs better even compared to the best supervised state-of-the-art models. What you see at the bottom are scaling curves. So essentially what happens, what you see here is essentially the right one is the scaling curves. So 8 billion, 62 billion, 540 billion. And the axes are the 6 different tasks. What you observe is that, yes, as you increase the scale of the model, of course, you get better blue score. So this is a 10 blue circle, 20 blue circle, 30 blue, 40 blue circle. So as you increase from 8 billion to 540 billion, well, it sort of moves from an average 20, 25 blue circle to more like a 40 blue circle, okay, across different languages, as you see. Right? Now, also what you see here is comparison across various models, Palm 540 billion, GPT-3, Flan, Lambda, and what you observe is Lambda performs the worst. In fact, right, it's very clear here, GPT-3 is the next best, Flan is okay, and then 540 billion, Palm 540 billion is the best. Okay. So scaling Palm from 62 billion to 540 billion in leads to several drastic jumps in blue scores. Right? So that's that. Translation quality is better when translating into English rather than out of English. So what you also observe is that the translation quality in general is better when you want to translate into English compared to out of English. Zero-shot prompt, here when we're showing zero-shot prompt results, well, it includes a score. I mean, the way it is done is that in the prompt itself, you put in the source and the target language names in the prompt. While in the one-shot case, you actually one-shot in the few-shot case, you actually don't include the language names. You just give examples. That is why you observe that in some cases you actually get better results with 0-shot rather than 1-shot. So the language names essentially, in some senses, actually is helping right here. You also observe that kind of thing happening in these results. Palm sort of seems to perform good even for low resource languages or direct conversions rather than direct language translations rather than going via English. Okay. So how does Palm perform on multilingual NLG tasks? So in fact, they experimented with 2 different multilingual NLG tasks, summarization and data-to-text tasks. And these data sets have been taken from the GEM benchmark, Generation Evaluation and Metrics benchmark. Right? So 4 of these are from data-to-text tasks, and then you have several of those summarization tasks. these tasks vary in what you want to summarize and finally get what kind of a summary. So for example, MLSum is summarize a news article, Wikilingua is summarize step-by-step instructions from WikiHow, XSum is summarizing news articles but in a single sentence, and so on. So there are several such tasks. Given a set of key value pairs, describe in 1 or 2 sentences. Given a dialogue context, summarize it, verbalize a subject, subject, predicate, object pairs, and so on. So several such interesting tasks on which PaLM has been evaluated. So this one verbalized task is basically you have like fact triples, like subject, predicate, object triples, and you want to write 1 or more sentences in a grammatical and natural way. Right? So on each of them, what one shot results and fine tuning results are shown. Right? So one shot and fine tuning results. For few shot results, essentially, summarization essentially is done by using this prompt, summarize the following article, and data text is done by using this prompt, verbalize. And then this was, of course, translated to the appropriate language if the input language is different. So what is observed is that PaLM 540 billion is actually better than prior state of the art on all English summary generation tasks. So if you basically look at this one, zero shot model is actually better than all of those prior, Lambda model essentially. In fact, on English generation tasks, summarization tasks, PaLM model is actually better compared to any prior state of the art or T5 model also. On others, it is sort of comparable and sometimes slightly worse, but at least on English summary generation tasks, PaLM model actually leads to really state-of-the-art results. They also experimented with another multilingual NLG task, which is basically question answering on the TidyQA Gold P data set. And they compared with MT5XSL and PyT5XSL. And what they observed, they basically compared again in fine-tune and few short settings across several languages. And what you observe is that there are large improvements from the 8 billion model to 62 billion model, but small improvements, from 60 to 540. But then what you also like nicely see here is that although by T5 is better on average, but a PaLM 540 billion model is clearly way better compared to the MT5 model. Compared to the MT5 model, at least PaLM T5 is actually much better. So that's that about multilingual handling by PaLM model. PaLM is PaLM memorizing data, right? So when you talk about very large models, you're always very you need to be very cautious about overfitting, right? So large models can memorize or overfit to data. So therefore, they basically try to figure out are there copyright issues in terms of the output that PaLM model generates. Okay. So therefore, they do 3 different experiments. In the first experiment, they try to look at different model scales, 8 billion, 62 billion, 540 billion, and then they check how much of the, if I basically take some sentence from the training data and I tell it, hey, complete the sentence, how many times it is going to come up with the exact generation versus changed versus different generation. So they compare on training data and held out data. And what is observed is that in about 2% of those cases, essentially, PaLM model actually memorizes things and spits out exactly the same sentence. But then in held out data, effectively, this kind of a thing is less than 1%. So this kind of a behavior of spitting out exactly the same text is actually a little less, right? About less than 1%. So held out data is, held out data is actually from the same distribution as training, but was not exactly seen in training. So, but then it turns out, this is not like it could have copyright issues. So what is happening here is that some held out examples are actually very similar to training set examples. For example, some boilerplate open source code license where only the year is changed. So that is that. So therefore, even though you see that 1% of it is sort of memorized, it's not like it's copyright and thing that could be causing an issue. It's probably licenses which are standard text, which is repeated over and over so many times. In the entire pre-training corpus. So in the second experiment, they basically checked for strings which co-occur a lot in the entire training data. And then they checked how many times PaLM model can memorize that. So they varied from, a string occurring just once in the data, example seen just once in the data, was the example seen like 100 times in the training data. And then, of course, they also scale with respect to the model size. So what you observe is that examples seen exactly once in the training data have a memorization rate of just 0.75%, very small, even for the largest model. While examples seen 100 times or 500 times, even larger, right? 500 times in the training data have a memorization of over 40%, right? Larger models clearly have a higher rate of memorization, but yeah, if something repeats like 500 times, the model learns it really well, memorizes it really well. In the third experiment, they tried to figure out what kind of domains have a higher probability of memorization. So they look at web, wiki, social media, news, books, and code, which are the parts in the pre-training data, and they observe that the code corpus has a significantly higher probability of being memorized. This is because the code corpus contains a lot of boilerplate licensing strings, shared code snippets copied from elsewhere, and automatically generated code. Uh, on the other hand, if you look at books, well, memorization is so low just because the book's corpus primarily contains truly unique strings of text, and therefore memorization is low. So what kind of explanations can you generate from the PaLM model? Right. So here are some interesting explanations about explaining a joke. Remember, these can be generated because of chain of thought prompting. So explanation of jokes or logical inference tasks. Let's look at the kind of explanations it generates. Okay. So let's look at this one. So of course, you can read up later by pausing the video here, but I'll just look at a few. So I was going to, so the input is this. I was going to fly to visit my family on April 6th. My mom said, "Oh, great, your stepdad's poetry reading is that night." So now I'm flying on April 7th. So the joke, I mean, what is the joke? Explain the joke. Well, this is explanation. The joke is that the speaker's mother is trying to get them to go to their stepdad's poetry reading, but the speaker doesn't want to go, so they are changing their flight to the day after the poetry reading. Right? So that's a very, very clear and a nice explanation of the joke. These all examples are very nice. Of course, they're cherry picked as well, but at least they work really well. Okay. Now look at this one, right? So this is about logical inferencing. So Trevor has wanted to see the mountain with all of the heads on it for a long time. So he finally drove out to see it. What is the capital of the state that is directly east of the state where Trevor is currently in? So now look at the awesome intelligence in the output, right? The mountain with all of the heads is on it is Mount Rushmore. It could figure that out. Mount Rushmore is in South Dakota. It could figure that out as well. The state directly east of South Dakota is Minnesota, another logical step of reasoning. And then capital of Minnesota is St. Paul. So you see 3 or 4 steps of reasoning so as to get the right answer from the hints given in the question. Yeah. Uh, and so on. So if you look at these, you will basically be surprised by the kind of logical reasoning chains that PaLM model could discover and put out as nice natural language explanations. Okay, so now let's talk about how is PaLM model biased. So how does it do on the bias and toxicity benchmark? So we look at the Winnow gender benchmark, which measures gender bias in English occupation nouns such as nurse and electrician. So you would expect nurse to be a female, electrician to be a male, and so on, right? If you basically keep stereotypical biases in mind. So in this data set, there are examples of this kind where you basically give this input. The nurse notified the patient that his shift would be ending in an hour. His refers to what? So these are co-reference resolution examples so as to test for bias with respect to either the occupation or essentially another referent noun. So what you observe here is that if you ask a model and it has like several classes to select from, it can select probability of a nurse is this much, probability of a patient is 0.0197, and here the model is doing good because his refers to nurse, rightly so. Okay. On the other hand, if you look at the ground truth, well, the ground truth is nurse, and the probability of nurse should be greater than probability of patient. So this is good. The model is doing perfect here. So if the generated stuff is this generative prediction, A, the patient, B, the nurse, C, the shift, D, the R, right? So since it is saying patient, essentially the model is doing wrong here. So that's that. So that is how the model is evaluated. The model can be evaluated on multiple choice question scoring kind of a scenario or generative scenario. Okay. So this is how the model is evaluated here. So either using multiple choice scenario or generative scenario, right? I mean, as you see, multiple choice scenario can actually give brownie points to the model, or the model can be considered as winning, even if the probability the correct answer is very low. So this has been compared. 540 billion model is compared to 62 billion PaLM model. What you observe is 540 billion model actually gets better accuracy, which is nice. It's still worse than human accuracy, but still good. It's still okay. Yeah. So that's that. Well, so it's okay in the sense that it's better than state of the art. As you see, state of the art is worse. So PaLM 540 billion gives state of the art results with low bias in them. Okay. So x-axis here is number of shots. So how many examples do you need to give to the model to understand that, yes, this is a biased task. So be careful about answering things. Okay. So that's that. Now, the data set, gender benchmark data set has three parts to it. The, essentially the male part, female part, and the neutral part. So in general, or rather, I would say the stereotypical part, the gotcha part, and the neutral or the overall part. Okay. So stereotypical part basically means that if I was following the stereotypes, I would basically get a good score for the model. That model will predict accurately. Okay. So stereotypical part would say the nurse notified the patient that his shift would be that her shift would be ending in an hour. What does her refer to? That's basically stereotypical female kind of a part of the data set. While gotcha part of the data set is exactly what you see here. So this is basically the gotcha part where stereotype would be nurse should be a female, but well, the answer expected is patient is nurse here, although it is his. Right. So of course you would expect models to do worse on the gotcha part and to do better on the stereotypical part, and which is what is observed here. So which is what you observe. The nice part is that well, the model does not perform that bad even on the gotcha kind of scenarios, right? So, and yeah, there is room to cover with respect to human baselines, but well, it's not as bad. In fact, it is better than state of the art. That's the nice benefit. Um, Now, thinking from a toxicity perspective, so how many toxic things does the model generate? So it has been evaluated. This has been evaluated on the real toxicity prompts data set with using and the toxicity is evaluated using Perspective API. So Perspective API gives you a score between 0 to 1. And this is what is plotted here. So if the input prompt basically had some toxicity, so what was the toxicity in the input prompt, right? And then you use it to generate text. So what is the total toxicity probability of continuation? Okay. So this is a human baseline. So and these are what the models do. So there's different scale of the PaLM models. So what you observe is that yes, the green line is actually better because even if you have low as you increase the toxicity probability of continuation increases, which is obvious. But with the green line, well, the toxicity generated is smaller. Okay? Compared to the 540 billion parameter model, where toxicity generated is slightly larger. But well, compared to many other models, this is reasonably okay. Yeah. And of course, if you observe, the toxicity generated is about 25%, but only in examples where the input prefix is almost is 100% toxic, right? Where the input prefix is not toxic, very, very little toxicity, then the toxicity generated in the output is also not that high. Okay. They also did a toxicity evaluation in terms of taking standard, races and religious groups and so on, and asking the model to generate completions and then measuring how much toxicity exists. So for example, you would observe that with the races, some of those races like Islam, right, you observe that the average toxicity is pretty high, about 30% toxic. But many other typical, typical scenarios like Buddhism or other kind of scenarios, you would observe that the average toxicity is pretty low compared to toxicity for religious groups. So there is bias, some religious groups, right? So there is bias, but then it is better compared to other models existing at that time. Okay. So in summary, let me now quickly summarize this video. In this video, I talked about the PaLM model, which is a 540 billion parameter dense transformer decoder language model trained on 780 billion tokens of high quality diverse text consisting of books, Wikipedia, code, social media, everything. Right? So there are three checkpoints: 8 billion, 62 billion, 540 billion, right? That they trained, and they trained them using their pathway system. That's why it's called pathways language model. Using a very large infrastructure of 6144 TPU v4 chips spread across two different pods and 768 into two different hosts on those pods, of course, connected by a high-speed, high-bandwidth Google data center network. The model has been shown to be really awesome at various NLP benchmarks. So it produces SOTA few short learning results on hundreds of, on around 100 of, NLU and NLG benchmark tasks. It led to steep performance increase for big bench tasks, does nice at multilingual NLG, source code generation capabilities as well. And the most interesting part was it can generate nice explanations using chain of thought prompting for explaining jokes and logical inferencing and so on. Yeah, I mean, as you increase the size of the model, you do see lots of new capabilities coming up, lots of diverse capabilities coming up in the model with respect to NLP, different forms of NLP. Okay, that's it. Hope you liked the video. Thank you for watching. Here is my LinkedIn, so connect with me and look at my research on my homepage. Thank you.